Alrighty, here is a series of videos where I'm going to go over a practice test that is on exponential functions and logarithms. And this first video is sketching various exponential functions. Now for these, I'm sticking with, for the ones I put here, I'm sticking with the base 2 for the exponential function. And that's a really good one, I think, to start off with because you can sketch the graph pretty easily simply by plotting points. And the thing is, I don't want to go to that much because I already did that in class, but you can plot some points here with x and y where you put in 1 for x. Okay, now what am I doing here? I'm going to sketch the graph first of 2 to the x. Sorry, I didn't make that clear. First, I'm going to do the graph of 2 to the x, and then I'm going to look at this translation of y equals 2 to the x. So this is just a little side project I got going here, and you know very well wouldn't need to do this if you already knew this guy here, if you knew how to do this already. But I want to just do a little review of what y equals 2 to the x looks like. And so I'll just put this off on the side in the corner. Okay, so if you look at 2 to the 0, that's 1. 2 to the 1 is 2. 2 squared is 4. I'm already off the page if I go 2 to the third power is 8. But maybe I'll make room. Okay, 2 to the third power is 8. So can I do that? 5, 6, 7, 8. And now 2 to the negative 1 power is 1/2. 2 to the negative 2 power is 1/4. Okay, so I mean, when I first went over this in class, I made a chart plotting the points, but that's like another chart. But you can, you can simply, I think you can, do I have to make a chart? You can just sort of do this in your head, or even this part here. That sort of looks messy. Like, why can't I just read this and see what there is? Okay, now, maybe I'll do one more though. Right there. Okay. Now the thing is, when I add 2, this shifts the graph up by 2. So I'm going back to our, to the star of this, what we're supposed to be looking at here is this graph over here. So if I look at y equals 2 to the x plus 2, what that does is it shifts everything up by 2. And I'll start by showing that the horizontal asymptote has been moved up by 2. And especially I want to focus on the y-intercept. That's moved up by 2. And you can plot points again. I mean, that's what's so good about base 2. There's other bases like base e. E is a really, really important number. It's a constant. It's between 2 and 3. It's around 2.7. And that's used in calculus. And you sort of need to study some calculus to see the significance of why you'd even want to use a number that's like, number e, which in terms of just purely plotting points, if you had base e to the x plus 2, it would be less convenient, but the graph looks almost the same. So 2 is a convenient base, but there's other bases, especially if you have a base greater than 1. And I guess sort of rambling on there as we went over this. So what I would say that I want to really focus on, though, is the y-intercept is 1, and the horizontal asymptote is y equals 2. It's increasing. If you change this from base 2 to say base 3, it's not going to look that much different. I mean, you could try sketching that. Or, it's not going to be like that much different. As long as the base is greater than 1, it doesn't look that much different, especially if 2 to the x, 5 to the x, as long as the base, in this case base 2, if it's greater than 1, it's going to be increasing. It's going to have a horizontal asymptote, the same, and which is y equals 2, and have the same intercept 0, 1. Now, let's then do a little side deal here with y equals 2 to the negative x. Okay, now if you remember, I'll write this down. Y equals 2 to the negative x. Now, if you remember, if you replace the x by negative x, it does a reflection around the y-axis. And so the graph above is y equals 2 to the x, me just make that a little darker or something. And this is the function y equals 2 to the negative x. So let's see how they compare. They look similar, except this one's decreasing. And it's like I said, it's a reflection around the y-axis. And I don't really have enough room to go all the way up to, any higher than that. Actually, let me, first of all, get a darker, bolder color here, or bolder marker. Okay. So that's how y equals 2 to the negative x looks, roughly speaking. I mean, because and also what you can do is you simply plot points. That's why I'm picking this base 2, is that if you want to break down and just say, okay, let me plot some points, I'll do that. Then that's why I like base 2. That's sort of, okay, let me just do that. All right. Now, what if I have the same graph, but now I'm subtracting 3? So this goes down by 3. That's true of any function. If you have, that's what happens to the graph of function. If you subtract 3 from the function, it'll go down by 3. While this guy over here, if I have the plus 2, it goes up by 2. So those are just shifts. Okay. So, well, I need to sort of wish I had maybe different graph paper that's a little smaller. In squares might be a little smaller, which I can do. I guess I'll just stick with this though. Why don't I stick with the purple theme? So you just take this graph on the right and you shift it down by 3. So especially what you want to take notice of is that the intercept is moved down by 3. So on the right here, I should have labeled this. This is way better if I label this. 0, 1 is the y-intercept for 2 to the negative x. So if I take 1 and subtract 3, I get 0, negative 2. And, okay, I'm sort of switching. Okay, let's get to the same colors. And so you just really sketch the same graph, but you shift it down by 3. So it's not that brilliant, really. I mean, it's just, you have to know the graph y equals 2 to the x, y equals 2 to the minus x. Then you either shift up or you shift down. And of course, maybe you don't know anything and you just plot points, but I think it's better to really, I really think it's better to have an idea of what these graphs look like. Now for this last one, we're multiplying by 3, and what happens is we take all the numbers in for the function y equals 2 to the x, and we multiply them by 3. And see, the horizontal asymptote for y equals 2 to the x is the line y equals 0. Now, it's not, you don't really multiply a horizontal asymptote by 1, but I'm going to say that you can sort of do a little trick to remember it that way, is that we can see that we're multiplying all the y values by 3 and including the horizontal asymptote, even though a horizontal asymptote doesn't really get multiplied by 3. But now you go to 0, 1, that's that y coordinate 0, 1. If I multiply 0, 1, if I multiply the y coordinate by 3, I'm way up here, it's 0, 3. And then I had negative 1, 1/2 multiplied by 3, and I get negative 1, 3/2. I didn't show it here, but you would have negative 2, 1/4, and multiplied by 3, 3/4. Negative 3, 1/8 multiplied by 3 is 3/8. So the thing also, what you see is that you still have this same shape, and you still have the same horizontal asymptote. What this does is that we can see just by plotting points that if I put x equals 0, y is 3. So it stretches this out so that I have 3 is the y-intercept, which is important because that's the initial value, or when you have time, or t equals 0. But we didn't really bring in t here. This is x, but it's an important thing to what happens when x is 0. But the horizontal asymptote doesn't change. So let's sort of compare this to number one, the problem number one, problem number three. Here on the problem number one, we have 2 to the x, and we add 2. So the whole thing shifts up by 2. So on the right, I did a little graph of y equals 2 to the x, shifted up by 2. But on number 3, I'm taking y equals 2 to the x and multiplying by 3. That stretches it out by 3, but it keeps the same horizontal asymptote. All right, I think those are 2 good examples of, or 3, where we're sketching graphs and showing translations of these exponential graphs. All right, I'll end there.